Hi everybody, this is Nikhil. So as I was telling, today I will discuss about this concept of grid management on 5th April 2020 9 p.m. See, as you know, the Prime Minister has announced that on 9 p.m. on tomorrow 5th April that all the fellow Indians must switch off their lights and we need to come out and light the candles or torch lights or flashlights, whatever you have with you, as just to express as a strength of unity of the entire country that we all are together and we all are fighting towards this corona. But still there are many comments that are running in the social media that is it necessary, does it have any meaning? So it might be having some meaning or not. That is an individual perspective. See, some might think that yeah, what he's telling is good. Some might think that what is this nonsense, something like that. But whatever it may be, he is our elected leader. We have elected him and we know that he is working towards us very well. So he has just humbly asked us just to give 9 minutes of your time. So can't we do that? Whether it has got some meaning or not, can't we do that? Yes, I think we could do. So I think definitely we all should support. But immediately after he has made this decision, immediately in the social media and all, one news in the form of electrical engineers notice has started to circulate that already the power system load has been decreased. If you are going to switch off the fans and lights and all, it is going to lead to grid blackout or grid failure. This kind of notice has been circulating, and that you have to switch off your light, but at least switch on the ACs and fridges and all. Such kind of things are there. So, from an electrical engineering perspective, I am going to discuss what are the effects of this decision, what is going to happen, and what is the practical data that is available to us, and all these things I will be discussing anyhow. So, my video is not going to be for electrical scientists or hardcore gate aspirants, but this is meant for every electrical engineering student who is a very average or below average student also, because I am going to discuss very broadly. I am not going to discuss into much formulas and technical, because there are many guys who are waiting for this video. Not everybody will be having that much idea about these equations and all, unless somebody who is preparing for the competitive exams and all. So I will discuss very broadly. This might be a little bit lengthier video. Why? Because very interesting video, lot of factual things that I am going to discuss. Because see, so far you might have learned about power systems, grid management, reactive power and all from your books point of view. But today, one decision taken by the Prime Minister, one thing that is going to happen commonly in the country, how it is going to affect and how our subject will help us understand in this situation is something very interesting for us. We must understand. So I will try to discuss, I will start to discuss now. So as you know, power system, this is everything is a power system. What do you mean by power system? Generate power, transmit and distribute. That's what a power system is. So I will broadly discuss the objectives. Okay, the objectives of power system. Objectives of power system is to generate power. Generating is not the objective. Generating at low cost, at a minimum cost is important. So that is one objective of power system. Next, transmit the power through a long distances, transmission lines. Merely transmitting is not enough. Transmitting at a low cost. What I mean by low cost of transmission is that the power lost in the power transmission line must be minimum, with minimum losses. And after that, efficiently distribute to each and every consumer, distribution lines. And distribution also at a low cost, in the sense less technical and non-technical losses and all. And just distributing perfectly without loss is not enough. You are supplying consumer to whom? You are supplying power to whom? To us, consumers. And we should get this power. Having continuous power supply is okay, reliable power supply. But how should that power be? It should be a quality power supply, isn't it? So what are those indexes or what are those parameters that will decide the quality of electrical power that we will understand? Because the effect of switching off all the lights or all the loads on this 5th April is going to impact those indexes, and they are very important. And the entire idea or the entire action of this power utilities or system grid operators is to manage those elements only. Now we will see, first we will derive what is the problem that we are going to get. So first we will study about quality index of power. We call it quality indices or quality indexes of power, whatever. So two indices are there. First index is voltage, system voltage. Other index is the frequency. Like our human body is having what? The immunity system. Let us say if your immunity system is not there, it doesn't work. Do you think the next second you will be alive? Definitely not. Because every moment, even now, millions of bacteria, a lot of viruses are still present in your body trying to destroy you. But the immunity system keeps on fighting at every moment. Understood? So the moment the immune system is not there, your collapse, your breakdown, your finish, your failure. Similarly, every electrical system, every electrical apparatus, say it mobile phone in your hand, or your AC, or your fan, tube light, whatever it may be, or a big power transmission line, or a generating station, all are electrical devices only. They also have got its own immune system. What is that immune system? Not protective gear and all. Inherent immune system. That is insulation. Insulation is like immune system to the body. And if there is any problem in the voltage variations, at the extreme level, it will impact the insulation of the apparatus, and ultimately if insulation is failed, then death of that apparatus. Electrical apparatus will fail. And if voltage is varying, not that extreme, but it is varying, your load will not operate satisfactorily. You may not utilize your apparatus very satisfactorily. It is not satisfactory. Now we will talk about frequency. Frequency, even if the frequency is varying, what happens? See, whatever power you are generating here, 90 power of the power consumption is in motoring loads. 90% of the load is motoring load. Motoring load means which takes electrical energy, gives our mechanical energy. And motor has got some speed of operation. If the supply frequency is varying, speed of operation will vary. And then what is the use of having a reliable, where is the concept of reliable motoring? Reliable motoring is when your speed is at the declared value. If your speed keeps on varying, let us say I have put my fan on speed 5. What if it comes to low speed and it keeps on going up high? What is the purpose of using a motor? No. So even here also the load functioning will be disturbed. So not just this aspect, there are many other things that we can discuss, but I just don't want to go into much deep technical details, but a broader or a basic thing I want to discuss, right? Frequency. So that is one action of frequency. Another point of frequency we will see. We all are having an interconnected system. This is entire power system is an interconnected system. What do you mean by interconnected system? See, interconnected system means having a grid, having a common grid itself is an interconnected system. Now let us say this is India. I am not perfect in drawing the India map. Just bear with me. Something like this, isn't it? India is something like this. So India, each and every state, there are many states, and every state has got its own generating systems, isn't it? All generating systems. So let us say now I am in Telangana state. Telangana state also has got some couple of generators, generating stations, and all those generators are connected where? In parallel. They all are connected in parallel. So parallel connection of all generators of a state is called as a state grid. What it is called? State grid. Interconnected generators itself is a grid. So Telangana is somewhere here. There is Andhra state, Tamil Nadu, Kerala, Karnataka. These states are there. So every state has got its own state grid. So if you interconnect the state grids only, that becomes a regional grid. So here is the south grid, south region grid. So like that, in India there are 5 regions. Northeast region, you are having a north region, you are having what? Eastern region, you are having western region. So in India, there are how many grids? 5 regional grids are there, and all grids are interconnected. These all are links connecting all the grids. All grids are interconnected. So this concept of interconnection, I will explain with a basic example. Let us say I am having a bike. Bike has got a wheel, and the wheel has got some spokes like this, isn't it? Initially the bike wheel is at rest. I will go and I will catch it. I will catch one of the spoke and I will start rotating the bike. Let us say I am rotating at some speed 2 kmph. I am rotating at a speed at 2 kmph. Now I have started the bike. I have what? Started the bike. I will suddenly accelerate to 50 kmph. Now the wheel will try to rotate fastly. I am catching this and rotating at 2 kmph. What will happen at this moment? Can you tell me? Your hand will break, isn't it? Or let us say already the wheel is rotating at 10 kmph. I am constantly accelerating at 10 kmph. You also comfortably caught it and you are rotating at 10 kmph. Now I got tired. I don't want to rotate. If I drop my speed, but the wheel is not dropped, the wheel is rotating at 10 kmph, what happens? Again my hand will break. This is what called as interconnection, synchronization. So every region is nothing but representation of a combination of generators. Every generator has got its own speed called as frequency. Okay, let us say south region generators all are operating at 50 Hz frequency. That means 50 Hz speed. You can interconnect south region with any other region only if their frequency or their speed is also 50 Hz. Same case. If any of the side will not maintain constant frequency, that will lead to what? Failure, break of your hand. That is what called as grid failure. So that is also again importance of frequency. If you are able to maintain constant frequency, then only you can have an interconnected system. What is the advantage of interconnected system? Let us say south region is having power deficit, and let us say west region is having power surplus, excess power is there. You can transfer power from there to here through this link. So many advantages are there. By having this kind of a system, what will happen? Basically, there are many advantages. One advantage is power flexibility. You will have a cheap power source available, cheap availability of power, and reliable power availability. All this kind of remote connectivity. Many advantages are there. I am not going to go into much technical details. So I hope you understood what is the importance of this grid and interconnectivity and all, right? Next, when we talk about voltage, regarding voltage, there is one Indian electricity rule from Indian Electricity Act, which will actually specify, as I told you, voltage cannot vary as much as it wants, which will limit the voltage variation. So that IE rule is 54. It's called as IE rule 54. Similarly, frequency also cannot vary as much as it wants. It is also specified how much frequency variation is specified by IE rule 55. I am not going to discuss what are the mentioned parameters of the IE rules of both frequency and voltage, but the variation percentage that is indicated as per Indian Electricity Act are too vague, are too wide. So practically if you maintain in those levels, definitely the grid will not be sustained. So we will go with international standard, IEC standard. As per IEC standard, the voltage variation allowed is plus or minus 5% in case of medium voltage and low voltage circuits, and in case of EHV circuits or HV lines or transmission lines, plus or minus 12.5% voltage variation is allowed. And as per IEC, frequency variation allowed is plus or minus 1%. If you take IE rule, frequency variation is plus or minus 3%. But still we will go with IEC rule only. Of course, the Electricity Act says that one. We will go with IEC rule only. Now we will try to understand what is going to happen tomorrow at 5th April. Now, consumers, we are consumers here, we are demanding some power. This is an AC power system, isn't it? So AC power system means what are the types of powers? We will be having active power plus reactive power. We will be demanding what? PD means active power demand, QD means reactive power demand. Demand means we are consumers, we are demanding. Why do we require reactive power? As I was telling you, we have motoring loads. Motors need to operate based on production of magnetic flux, and magnetic flux is produced by a power called as reactive power. Okay, so reactive power demand is there, at the same time active power demand is there. So definitely to satisfy the demand, there should be active power generation as well as reactive power generation. Active power generation and reactive power generation, right? Now we will see how this active power and reactive power and voltage and frequency are related. Okay, so here I will go with one principle called as the principle of decoupling. I will not go into detail what does this principle of decoupling means, but now I will tell you that the voltage of power system depends upon the reactive power. It's not directly proportional, I am telling. It depends some or the other way on the reactive power. At the same time, frequency, this is another power quality index. Frequency depends upon the active power. What is the reactive power? Means reactive power mismatch. Frequency depends on active power mismatch. So first we will take the case of voltage. What I mean by mismatch and all. See, I am generating some amount of reactive power, and same amount of reactive power is being demanded by the load. Absorbed, net reactive power 0. Very good, happy. Voltage remains constant as much as it was. Let us say 1 per unit voltage is there. 1 per unit voltage will be there. No problem here. I have no problem, you have no problem. Reactive power generation is there. Reactive power demand is more than the generation. More reactive power demand on the generation means what? More motoring load, more inductive load on the system. If inductive load will increase in the system, what happens to the power factor? Power factor will fall down. If power factor falls down, what happens to the current will increase? If current will increase, what happens to the voltage will drop? That means the voltage will be decreasing if you are having this case. Next case, if generation is excess than the demand, that means demand has fallen down. What is going to happen? So this is one problem that we have identified that is going to happen tomorrow. What we are going to do, we are going to cut off the loads. That is what is going to happen. Yes, you might be getting some contradictory doubts now. Just wait, I will clarify everything. So excessive reactive power demand as compared reactive power generation as compared to demand. What will happen when it will lead to voltage rise? How can you say, sir? Now what I will do is I will equate this reactive power to salt in your body. What happens, guys, when you take more salt in your body? Just tell me, if you take more salt, what is going to happen? Your blood pressure is going to increase, isn't it? More salt, more blood pressure, BP. Blood pressure, power system, what is the pressure? Voltage, electrical pressure, voltage. So if more salt, that means more reactive power, more voltage in the system. You are injecting excessive salt in the system, but there is nobody to eat that salt. What happens to the voltage? Ultimately it rises. Now if voltage rises, high voltage surges will come. So maintenance of voltage, again this becomes a criteria. So this is one very important problem that we have seen. Voltage will rise. Now when you talk about the peculiarity of this problem, see 9 p.m. 9 p.m. is going to end, this phenomena is going to end, isn't it? This activity is going to end. So let us say up to 9 p.m. the load on the power system will be somewhat high because everybody will be switching on all of their loads and all. At 9 o'clock suddenly the load is going to drop. That means active power, reactive power demand both are going to drop. Still again you might be getting some contradictory doubts. Just wait. Up to 9 minutes no load, and after 9 minutes the load will shoot up. Within a very short span of time the load is going to increase. See, generally demand varying generation we can adjust and we can maintain. Here the challenge is the time. You have given very little time. When this 9 is open, when this 9 is completed, everybody will switch on at the same time, almost more or less. Now here the time margin that you have got is very challenging. Managing the variation in the load is not a problem, but the rate of change of load, the rate of addition of load or rate of fall in load is important. Because within a very short span of time, within seconds, within a less than a minute only, the entire nation is going to decrease its load or the entire nation is going to increase its load. Here comes the issue. So if suddenly the generation has been increased, that means suddenly demand has fallen down. What happens to voltage? Suddenly it will rise. This is a transient phenomena. So rather than a normal steady state rising, the voltage will appear in the form of a surge. Immediately in the next second, the entire system will be subjected to what? High voltage surges. See, if such a high voltage surge will come, do you think what could be the situation of the power system? Definitely it will be subjected to some stress. You have to manage it. So in order to manage, what should we do? Excessive reactive power generation is there. Try to decrease the reactive power generation and introduce somebody who can eat up all the salt. So what we will do is, we will try to introduce something called as shunt reactors. We will use what? Shunt reactors. What is shunt reactor? If this is the transmission line, parallel connect one inductor. This is what called as a shunt reactor. Reactor is an inductor, consumes reactive power. So whatever excessive salt is there, this fellow will eat up everything. Connection of shunt reactors. Now the next question is, where is the location of this shunt reactor? Where is the location of this shunt reactors? So these shunt reactors basically present in the EHT substations. Generally 220 kV some places and 400 kV most cases strategic points of having this shunt reactors. Why is it so? Why is it so means we have to understand the voltage profile of the line. For this we have to understand what? The voltage profile of the line. So generally what happens is, normal conditions, let us say generating is generating some voltage 1 per unit, rated voltage, load side also voltage is 1 per unit, everything is fine and normal. Now let us try to plot the voltage profile along the line. Voltage profile along the line means what? How the voltage is varying along the length of the line, we will see. Normal, I am telling ideally, this dotted line represents the voltage profile of the line. That means everywhere along the line it is 1 per unit only. This first case. Next case, this case. This case. That is, demand is more than the generation. Now how will the voltage profile be like? The voltage profile will be like this. Voltage profile will be like this. In this second case, let us say this is case 1, case 2, case 3. Case 1, case 2. Voltage profile will be like this. Understood? Now this case, how is the voltage profile going to be like? Something like this. This is going to be the voltage profile like. As you can see, we will be just discussing about this case only. I told you excessive salt, excessive voltage. The voltage along the line is increasing in the between and it is decreasing at these ends. So you told that voltage will increase in the line, then why this asymmetrical distribution is there? I will explain you why this asymmetrical distribution is there. So in fact this should be something more like this, okay? It would be something like this. What happens is basically, here you have transformers, here also you have some transformers. At the generating side and at the consumption side, maintaining voltage is a very strict parameter. So you maintain voltage, whatever may be the incoming voltage, by using tap changing transformers. Of course, inside the line the voltage might be high. At the end of the transmission line, in the transmission substations, you try to pull down the voltage to 1 per unit. Of course, the incoming might be high. Here also you will try to, here you are not going to do anything. Here you will be supplying at 1 per unit only. But inside the transmission line, what is there? Inside the transmission line there is capacitance. And all the capacitance will add up and the maximum capacitance is assumed to be appeared at the load end side generally. So what is a capacitor? Like reactor, like a parallel inductor consumes reactive power, a parallel capacitor what? It can deliver reactive power. So it will inject a lot of reactive power and hence at this point in the line you are having what? High voltage. You are having what? High voltage. Now there is another quality of this reactive power that you might already know. Reactive power always travels bidirectionally in a transmission line. It travels from high voltage to where low voltage is there. It always travels between a high voltage point to low voltage point. If you look at here, where is the high voltage point? Here is the high voltage point. And where are the low voltage points? I can say this area is low voltage. Just forget because this length is very little. So reactive power will be flowing where? In this direction. In this direction. And the voltage surge will be appearing like you are having a tsunami. It goes on like that. The voltage surge, a voltage wave will just move and will try to hit all the substations in the form of this reactive power. So reactive power is traveling from receiving end of the transmission line towards the sending end. Now I am telling that shunt reactors are placed where? EHT substations, 220 400 kV means this region of the transmission line, isn't it? So this is where we are placing the reactors because the incoming power is from there, reactive power is from there to consume that. Understood? I hope you're getting the point. So in order to save the entire power system and to bring back the voltage profile to normal, we will do this kind of corrective actions. So tomorrow also, all the big substations are going to gear up with this action of setting up the shunt reactors in order to manage what? The voltage rise. So to manage the voltage rise, what we are going to do? We will be needing what? Shunt reactors. At the same time, we will be needing somebody who will be consuming reactive power. So to consume reactive power, we are having shunt reactors. At the same time, we are also having fax devices like SVC and all these fax devices. So wherever there are fax devices, they will be kept into operation in a way to absorb the reactive power. And who else can absorb the reactive power? Generator also can absorb the reactive power. Is it, sir? How is it possible? See, synchronous generator in a power station will be operating at which power factor generally? Lagging power factor. What do you mean by lagging power factor of a alternator? When alternator is operating at lagging power factor, that means this fellow is delivering what? Reactive power. He is delivering what? Reactive power. But when alternator, and this happens at which condition? Overexcited condition. When you are overexciting the synchronous generator, it will start generating the reactive power and it will pump out. And the power factor would be lagging. But when you are under-exciting it, when you are going to under-excite this synchronous machine alternator, it will go into leading power factor and it will absorb the Q. It will start absorbing the Q. So every generator has got a limited constraint of how much amount of reactive power it can accept. That is determined by something called as capability curves of that particular generator. It will be provided by the manufacturer only. So according to what that capability curves of the generator says, that much amount of reactive power they will try to absorb. So tomorrow there are three ways to manage this problem. As you can see sidewise, that Telangana Transco has given some instructions. See, what does it say? And he says that, see, reactive power management that they are going to do. And if you look at below, reactors in service, you are requested to ensure reactors in service and monitoring of voltage patterns at all substations and tap changing of power transformers suitably, opening of lightly loaded parallel EHT lines in coordination with SLDC. So, see, why do you have to open this lightly loaded transmission lines? Because lightly loaded transmission line, as I told you, the transmission line is having capacitance, is a source of reactive power, and it starts injecting a lot of reactive power into the system, and you are eating up the reactive power, and again reactive power is being generated. So this will again create a problem in managing the voltage. Therefore, whichever transmission lines are like redundant, you can transfer the load into other transmission lines, parallel lines, and which is lightly loaded, you can immediately disconnect, and by coordination with SLDC and all these things. That is what it says. I hope you got the point. Now let us move into the next case, that is frequency management. So like I told you, there might be some other contradictory doubts to most of you that, sir, already due to lockdown, as you told that, see, majority of the load on the power station is a motoring load, which is inductive load. Okay, sir, we will agree. But now due to this lockdown and all these effects, already in the power station, on the power system, most of the industries have disconnected, isn't it? Most of the industrial load has been cut off, due to which then majority of the load now on the power system is domestic load only. So domestic load means mostly lighting, resistive load only. So how can you say that the reactive power is going to be a problem now? How reactive power is going to be a problem now? See guys, this is, you should remove these kind of notions in your mind. When you talk about reactive power consumption in domestic, see, now this is summer period. You will switch on the fans. Fans is a load of reactive power, is a sink of reactive power. ACs all are the sources of reactive power. And tube lights. Even today, I can say nearly 70 to 80% of Indians are having the tube lights, old version of tube lights, not LED tube lights. And old tube lights are also sink of reactive power. That means they will also require reactive power. Why do they require reactive power? Because they have that choke, isn't it? That choke requires the reactive power. Like that, still reactive power demand is there. It is not gone. It is not gone off. Of course, the reactive power that will be changing due to switching off of lights and all will be very less. Here the problem is not about the magnitude, guys. Here is the problem with rate of change of load, rate of change of reactive power. Reactive power drops, voltage will drop proportionally, no problem. But if reactive power suddenly drops, if the reactive power sharply drops, sharp rise of voltage, high surge will be there. Here the problem is not with the magnitude. Here the problem is d by dt, rate of change of power. Understood? I hope your doubt is clarified. But still, there is not just loads who are consuming the reactive power, isn't it? Even the transmission line is a load of reactive power, if you understand. If the transmission line is also load of reactive power, isn't it? See, transmission line has got what? It has got some inductance XL, and transmission line has got some capacitance, isn't it? This line inductance will consume the reactive power. What is the reactive power consumed by the line? Current flowing through the line is I, then power consumed or reactive power consumed by this fellow I square into XL. If current in the line is decreasing, of course here there might be no reactive loads, much reactive loads, because industries have shut down, but still current will decrease or not due to this effect? Yes, current will decrease. If current will decrease, then the power consumed by the line will decrease. Yes, so this will again create a problem. And anyhow, this generation is constant, it keeps on generating. Now here there is not even this inductor ready to consume this excessive reactive power. So you cannot say that kind of a very hard and a very harsh statement, right? So I hope you have cleared your doubt. Now I will get into the frequency management. Now according to this principle of so-called decoupling, this frequency component depends upon what? Active power mismatch. What do I mean by active power mismatch? Active power generated is equal to active power demand. How much generated? That much demand. No problem. Frequency remains constant. What is the rated frequency? That much frequency will be there. Now active power generation is less than active power demand. More demand is there. Let us say you are going on a bike with a constant acceleration. Your accelerator some fixed position. Initially 2 members on the bike. Suddenly 4 members will sit. What happens to the speed? Will fall. That is what here. Generation is less than demand. Demand increases, speed of the generator will fall, frequency will fall. So this will lead to what? Frequency drop. Suppose if generation is more than demand, what happens? Opposite will happen, frequency will rise. But if this change of demand is gradual and slow, frequency variation will also be gradual and slow, and it would be easy to manage. But now it is sharp. Sharp means little bit challenge posing on the system engineers to manage this sharp variation of frequency. Like I told, India has got 5 grids: north grid, east, west, northeast, south grid. Like this we are having. Let us say people of west grid do not switch off immediately. Let us say they plan to switch off at, let us say, 9:01 minute. Let us say people of south grid, they immediately switch off at 9, or let us say 2 seconds gap. Let us assume 2 seconds of gap, or let us say 9 minutes 58 seconds, and these guys 9 hours 1 minute. Here 9 hours 58 seconds. How much gap is there between these both areas switching off their loads? 2 seconds is there. Now in this 2 seconds, what is going to happen? Here sharp voltage, here sharp rise in frequency is going to be there. Here frequency will shoot up sharply. This area is interconnected, isn't it? Here at this instant of 58 and 59 seconds, the frequency still is rated frequency. Mismatch of frequency. Here there is a chance that these both grids will disconnect, or failure of interconnection might be there. So like that, in an entire interconnected system, there is this kind of a challenge is there, because frequency will suddenly shoot up. So I hope you are getting what I mean. So what is the solution for this? So the solution for this is, generally whenever you are managing frequency using this active power and all this concept, you could either to maintain the frequency constant, we have to maintain the balance between active power generation and demand. So you could vary either the demand side or on the generation side in order to maintain this balance. So demand side maintenance is not your case. Here the problem is, so either you can maintain on demand side or you can maintain. So in order to maintain the balance between active power generation and demand, you could at least achieve variation or control over demand, or you can control over the generation. So here what is happening with the demand? Demand voluntarily people are shutting down. Now you can't ask them to switch on your loads, because so what can we do on the demand side? That is what we are going to see now. And what is that we are going to do on the generation side? That is what we are going to see now. This is going to be more practical and very interesting. So here also our problem is that generation of active power is excess to the demand. Now we will see how we can manage it. We can manage it on both sides. So we are having the power generation side and power demand side. So here what we want to do, in order to overcome the situation, we want to decrease the generation, because generation is excess. Now demand is falling down, but in order to balance this, what we have to do, desirable is increase the demand. We cannot increase the demand by asking consumers to switch on their lights, because they are going to switch it off. Okay. So what is that we can do? Artificially can we increase the demand? Artificially can we increase the demand? Yes, there is one possible way. What is that one possible way means? See, in hydroelectric power stations we are having what? Pumped storage power stations. Pumped storage plants are there, isn't it? Hydroelectric power station with pumping mechanism. I hope most of you might be knowing. So when this hydroelectric power station is not generating, what it is not generating? See, let me just basically discuss about this pumped storage plant. So let us say this is the dam, this is the head race, this is the tail race, and here water will be released, and generation will take place when water is coming from up to down. Power will be electrical energy output. Now after doing the generation, what I will do is, whatever water I have left down, I will collect this water and I will pump them back into the reservoir. This is what called as pumped storage. So whenever again generation is required, what I will do is I will release this water back and I will try to generate. This is what a pumped storage mechanism is. When you are pumping back, what the kind of action you are doing? You are doing pumping action. What is a pump? Pump is a motoring action. What does a motor do? It will take electrical energy as input again from the grid and it will do this pumping action. So all the pumped storage plants will be given a command, now start your pumping action. Pull the water, store it in the reservoir. By this what we are doing? We are trying to increase the demand on the system. That is what next step is going to be taken care by all the utilities now. So this is what going to happen now. Next, what is going to happen? Power generation demand. See, power generation should be decreased. So how should we decrease the power generation? Let us see what are all the power station plants that we are having. See, power plants are classified as what? Base load plants, and we are also having peak load plants. So base load plant means generally include thermal, we are having some nuclear, we are having large hydropower stations. Peak load plant means you are having gas power stations, you will be having non-renewable energy, you will be having what? Diesel, or some old thermal power stations, small hydropower stations. These all are peak load plants. Base load plant means the plant whose capacity is very huge and they are kept into operation almost every time, almost 24/7. Whereas peak load plants are not permanently connected plants. They will be connected as and when the peak load is there, whenever the load on the system is increasing. And the difference between base load plant and peak load plant is that peak load plants can be started immediately and can be cut off immediately. Whereas the base load plant, it is not that easy. But still we will see which of the plants can be started easily and cut off easily. And out of all of these, more rigid is thermal. Thermal power station takes 2 to 3 days to start. Turning off is okay. Something to destroy is very easy than creation, isn't it? So you can immediately cut off the thermal power station. But when you are abruptly taking off the thermal power station, whatever the heat that has been generated, whatever is there, all that heat is there. Heat has been lost. It will lead to ultimate losses a lot. When you are going to suddenly take off the thermal power station from the service, it will lead to a lot of thermal losses, thereby decreasing the efficiency, overall life efficiency of the power station. And another thing is, again, let us say for this 9 minutes you are going to switch off the thermal power station and immediately now the load is going to shoot up. Now the load is going to shoot up. When the load is going to shoot up, what happens to the voltage? Voltage will try to fall down. What happens to the frequency? Frequency also tries to fall down. A surge will be there. A surge of voltage drop or a surge of voltage drop, frequency drop will be there. So in that condition, you require generation or not? Yes, we require generation. Then what can we do? To the thermal power station. So here the problem is operating with the thermal power station. Next, nuclear power station. Nuclear power station, starting the nuclear power station itself is again a big task. It will almost take, sometimes it will almost take 1 week to 1 month also. So why is it like that? Means something called as criticality factor should be attained in order to stabilize the nuclear reaction in a power station, nuclear power station. So these both all are rigid. Again, when you talk about hydroelectric power stations, okay, immediately you can start, immediately you can stop. So you are having flexibility with hydroelectric power stations. Next, diesel power station. Diesel power station is just like a diesel generator that you have below your company or your apartment. And next is gas power station. Non-renewable energy will not be available at night 9 p.m. No non-renewable energy. Old thermal power station, again thermal power station, old or new, it takes time for starting and all. So for this time period, what we can do to reduce the power generation means anyhow non-renewable energy is not there, generation is already less. Now you are having hydroelectric power stations might be cut off. Diesel, gas, everybody will be cut off. Thermal cannot be cut off. But rather what we can do, we can control how much active power is coming out of the thermal power station by steam governing mechanism. We have already learnt about the steam governing mechanism. By this, we may try to reduce the steam output by giving the coal input or reduced coal input, and steam coming to the turbine we will try to control. And whatever power that is being generated in the thermal power station, we will try to balance by activating almost all the pumped storage plants in the system, and we will try to balance them. At that point of time. And if ever there is any electric battery storage system, let us say electric vehicles are there. Electric vehicles might be encouraged to connect. Okay, electric vehicles might be encouraged to connect their battery storage system at that point of time. And another thing is, see, almost all states in the country are providing almost free electricity 24/7. I think almost all states are providing like that. See, you are going to switch off the lights, but not the motor pump sets in your agricultural field, isn't it? So agricultural consumption will be there. So in this way, by cutting off these power stations which can be easily managed, we can try to balance this power generation and immediately power demand as well. So immediately at 9 p.m. power demand will rise. So immediately you will put into operation all these guys. Hydroelectric power station, pumped storage plants, everything. Pumped storage plant, instead of pumping, now it will start generating. It has already pumped a lot of water. It can immediately generate now happily. So you can manage it. But it is manageable. But here, what is the challenging aspect is the discipline or the timing is important. How the command is been given by the load dispatch centers to the generating stations, how they are shutting down or turning off, synchronizing their plants to the grid. This is one challenging aspect. But it is not that dangerous aspect. Yes, it is a critical aspect if not managed well. At the same time, it is manageable also. Why? Because this notice has come well before to arrange some plan and all these things. So this is all the technical aspects behind this. Now we will see some data that I have collected about how is the load demand, and we will try to analyze the demand, how it is going to be like that. So it is going to be very much interesting. Hi guys, now we will start our demand analysis for grid management that is going to happen tomorrow. So before that, we will see how was the situation on the day of Janata curfew, that was on 22nd March Sunday. So we will just compare the demand of the previous Sunday. This blue color line represents the previous Sunday demand, and we will see the load curve, how it was there all over India. So if you see the previous Sunday, we are having a peak load of around 153 gigawatts, and it has occurred around 9:20 a.m. of time, morning. And here if you see on the Janata curfew, the load has fallen down 135 gigawatts and around 6:30 a.m. in the morning, very early it has occurred. And the demand gap, how much demand has fallen down means approximately you can say 18 gigawatts has fallen down. 18 gigawatts means it corresponds to at the rate of 12%. That means 12% fall in demand was there on Janata curfew day. Again you see in south region, now we are in the south region because I am in south region. Telangana state. Now I will see how it has varied. So on the before Sunday, the previous Sunday, 48.3 gigawatts, 9 a.m. in the morning was the peak load. And if you see on the Janta curfew day, 42.2. That means approximately like you can say 6 gigawatts has dropped. And the load peak load has occurred morning 8 a.m. and 9 a.m. both times approximately. So if I can see how much percentage drop, it represents 12.5% reduction in the load. And strangely, if you observe on the Janta curfew day, the peak load of the day has occurred night 12:55 a.m. Night 12:55 a.m. at 44.2 gigawatts. Whereas in the daytime, you have got the peak load at 8 a.m. and 9 a.m. 42.2 was the daytime peak load. Right now, we will see the demand analysis of this week. Okay, because tomorrow is going to be that scheduled switching of lights of 5th April. So we will see. So we are having data of up to 2nd April. Okay, that is day before yesterday. We are having the data of total demand analysis all over India demand. Now first we will see what was the situation on 4 April 2019. That means the same day exactly last year. So exactly last year on 4th April, 169 gigawatts was the entire demand of the country, maximum demand of the country. You know what is the installed capacity of the country? Roughly 340 gigawatts. So 340 gigawatts is the total installed capacity of the country. And how much is the maximum demand that you are getting? You are getting 169 gigawatts as the maximum demand on 4th April 2019. Now we will see on 5th April 2019 it was 165 gigawatts. Okay, now we don't have data of 4th April or 5th April. Now we are having data up to 2nd April. So the same trend will almost continue. See, this blue color line represents on the last year 31st March to 6th April. That means 1 week, Sunday to Saturday. And again you see 15th March 2020 to 21st March 2020 is the red line. So these are past 3 weeks, and this violet color line is the present week which we are in now. You see, as compared to blue color, that is last year demand, each preceding week demand has been falling down, isn't it? The load curve is shifting downwards. And you see this, we are in the bottom one presently now, this violet color one. And if you see, there is some notable change over here. What is that notable change means? Let us say I am taking the last year curve. Last year curve, let us say I am taking this Tuesday. So this is the Tuesday curve. In this Tuesday curve, when is the maximum demand occurring in the day, in the whole day? In the night time. You see here also night time. So earlier when everything was okay, night time was the peak demand time. But if you see now, when is the peak demand? In the daytime. In the daytime, I hope you can observe the changes now. So anyhow, on 2nd April it was slight change. The night demand was little bit higher than the day demand. But you see, the demand pattern has been shifting. You must be observing all these things. See, okay, it was around 126 gigawatts. See, where is 169 gigawatts last year? Where is 126 gigawatts this year? That means I can say roughly the change is around nearly 25% of the load has been fallen down. 25% of load is dropped down. On the Janta curfew day, it was only 1 day people thought, but now it is the entire country is in lockdown. So all industries, everything have shut down. 25% of the demand has been fallen down. Only 25% has fallen down, right? And it is 126 gigawatts. And out of this 126 gigawatts, roughly 10 to 15% is only the domestic. Roughly 10 to 15% is the domestic that is going to expected to shut down tomorrow in the form of lighting load. If you take 10% of this, how much is it? Roughly 12 gigawatts. So if we were able to manage roughly 12 gigawatts, then definitely we will be able to withstand. 12 gigawatts means on an average, each grid, there are 5 grids in our country. So each grid roughly 2 point some gigawatts. Roughly 2.4 gigawatts is the load that is going to drop in each grid. South grid, west grid, whatever, all the grids are around averagely 2.4 gigawatts. So if we were able to manage this 2.4 gigawatts of load reduction, then it would be easy. So 2.4 gigawatts fall is only very little value, but the challenge is the time. As I was already telling you, the rate of fall of load is very sharp. Now if you will try to observe the south region demand the past 3 weeks, you see earlier how much it was. That is blue color. On the blue color it was CC 4/4/2019 48.5 gigawatts. But you see, before the Janta curfew the demand was much higher. Because in this 1 year of time, industries might have set up more, and like that, the demand has increased. And you see, the demand was something around 53 gigawatts, approximately 53 around gigawatts was there now. But if you compare the last year, it was 48.5 gigawatts. Now, if you compare this violet color one, this week on the 2nd April, day before yesterday, the load was 43 gigawatts only. That means if you observe, when you take from 53 to 43, we can say roughly 20% of load has been dropped in south region also. In the south region also 20% demand has fallen down. So how much is the demand gap that has fallen down? Around 10 gigawatts. When you compare with the present week, but when you compare with the last years, it is roughly around a demand gap of how much it is there, around 4.5 gigawatts demand gap is there. So if this is the graph that we have got from the National Load Dispatch Center website, and based on this, the management will be done what I have discussed in the previous section. Okay, that's it for this video. Thank you for watching, guys.